Today's screencast is on the reaction of weak bases with water. Yesterday's lesson we looked at the reaction with weak acids in water. So what we need to understand about weak bases and when we write their dissociation reaction is it's important in order for you to get the right reaction that you do remember to include the water in the reactant side, understanding that it is a liquid though, so it will not be included in your law of mass action. A weak base, reacts with water, producing its conjugate acid and the hydroxide ion. So here we see a weak base, CH3NH2, reacting with water. And we have an equilibrium formed here between its conjugate acid. Notice here this has one more hydrogen than the weak base. That's how you look at your conjugate acid-base pairs, how you pick them out. And there's your hydroxide ion. Remember, your weak acids and your weak bases will have K values, equilibrium constants, and the B here is just denoting that it's for a weak base. So here's the Kb value for this. So again, conjugate acid and hydroxide ion are the products. So if you set up your law of mass action for this reaction, you would include the two products. These are both raised to the first power. The equation is balanced. It's a 1 to 1 to 1 ratio. And then that would be over the concentration of the reactant here. And again, we do not include the water because it's a pure liquid. Remember, water is an important player in this reaction. However, we do not include pure solids or pure liquids in our law of mass action. Some common weak bases and their conjugate acids, and many students do struggle with identifying these. These are on your notes sheet, so I just want you to kind of compare the formulas for the weak bases and their conjugate acids. Notice the difference between the formulas is that the acid in the acid-base pair always has one extra hydrogen ion than the base. So notice the patterns that will help you. Also remember these Kb values are in the appendix of your textbook. So the reaction between weak bases and water, sort of a generic reaction for that, is we see here where B just stands for the formula for your weak base. Reacting with water, understanding that's liquid water because these are aqueous, in equilibrium with BH+. So notice this is his conjugate acid, and there's your hydroxide ion. Now, you could, with your weak acids, let me just remind you, like if you had an acid, this would be like your weak acid. Normally, with our weak acids, we just dissociate them HA in equilibrium with H plus A minus. So we didn't write the water here, but we understood that water was present to dissociate it. You could, if you wanted to sort of have some continuity between your the way you start these problems, you could react your weak acid with the water when you're trying to write the equilibrium. Just understand that the water is going to actually accept the hydrogen from the acid. The acid is going to donate the hydrogen to the water, and it's going to form the hydronium ion. Remember, the hydronium ion is the same as your hydrogen ion. It's just the hydrogen ion has a water attached to it. And then that would leave A minus behind. That might be something you might want to, if you just kind of compare this reaction with this one, because you've got to always write your dissociation reaction out. So this way, both of these would have the water in them. Here's your weak base, and here's your weak acid. Notice weak acids produce the hydrogen or the hydrogen ion and the conjugate base of the acid. Here's your conjugate acid-base pair here, and here's your base and his conjugate acid here. Bases produce hydroxides. So the law of mass action for a weak base dissociation would be represented, if you use this as your generic reaction, by Kb equals concentration of the BH plus ion to the first times hydroxide ion to the first divided by the concentration of your weak base. All weak bases do this. Do not try to complicate it. Don't try to overthink it. So let's look at this reaction. This says, what is the pH? So we're looking for pH again. Of a 0.5 molar solution of ammonia. So this is a weak base. And we know that because, well, ammonia is your most common weak base, but here we see there's a Kb value given, so this must be a base. First thing you want to do is you want to write your dissociation reaction. So remember, NH3 reacts with water in equilibrium, and it's going to form the conjugate acid, which is NH4 plus, because bases accept hydrogen ions, and he's getting it from the water. And when you pull a hydrogen ion off of the water, you do leave behind the hydroxide ion. So now we want to ice our problem. And since this is liquid water, I usually put dashes here because they're not included in the law of mass action. They're not going to have any effect here in your ice of the problem. So 0.50 molar is our given concentration of our base. And remember, in the beginning, there are no ions initially. Since there's no products over here, we know it's going to shift away from the reactants and towards the products. And since this is a weak base, just like with weak acids, you define your change or your shift in terms of x. So minus x plus x plus x. Now, remember the 5% rule. If you have an initial amount present here, you can neglect x for your weak acid and weak base examples. So we're going to pull down here 0.50 molar because it's not going to dissociate more than 5% usually, and this will be equal to x and x. So if you write your law of mass action, Kb, you would have concentration of the ammonium ion times concentration of the hydroxide ion divided by concentration of ammonia. So we know the Kb is given 1.8 times 10 to the negative 5 equals x times x over, and this is an approximation because we are neglecting x for the moment, 0.50. This will help simplify our problem because we're invoking the 5% rule. So now cross multiply here, 1.8 times 0.50, and then that'll be equal to x squared. And then take the square root of that. Now for simplicity and times, I don't have a lot of space here. I'm just going to go ahead and get the value for x, which is equal to our hydroxide ion here because this is a base. Always be aware of what you have. Solve for. And that's going to be equal to, if I plug it in, 3.0 times 10 to the negative third molar. So always check for your 5% rule. And if you check for the 5% rule on this, it is less than 5%. Let me just remind you for the 5%, you wouldn't have to show me that, but I would always check it. You take your x, which is 3.0 times 10 to the negative third, divide by your original concentration, 0.50 times 100. And as long as x is less than or equal to 5, then it's okay. 5%, excuse me, then it's okay to neglect the x. So now we can find the POH. POH is equal to the negative log of 3.0 times 10 to the negative third. So the POH is equal to 4.52. Remember, two suffix here means two decimal places here. And that means the pH is equal to 14 minus 4.52. So the pH of this solution is going to be 9.48, and that is ultimately what you're looking for. That's two decimal places because when you subtract, you go least decimal places. Again, make sure it makes logical sense. The pH of a base, NH3, should be greater than 7, and this is. All right. That is all for this example for this screencast.